Welcome to this lecture of microscale transport process. What we have been discussing was this electro spray, and at the end of last class what we were talking about is trying to find out this time scale for a DC electro spray. We discussed about this time scale. When it comes to the AC electro spray, we have another time scale that is featuring that is arising because of this AC time period or AC frequency. So, one has to ensure that this AC frequency is sufficient, that it is not merely causing just a local change in the meniscus, but not finally culminating to the formation of a droplet, or it is just it is not letting the this double layer to equilibrate fully. So, these are some of the things that needs to be understood. In this connection, what we were discussing was the RC time scale, and where we were at the end of last class was basically we were trying to show that there is a double layer has a particular model as far as this RC time scale is concerned. If one looks into the input signal stimulus, if one defines input signal stimulus this way, which is a very conventional one, not that one wants to, I mean that is the way it is very traditionally done. So, there would be a response signal which is given by this quantity. So, this is the what you call current response signal, and this is shifted with a phase difference theta. This current this signal is shifted by the phase difference this theta. So, this is how this this would be the response current, and in that case the impedance is traditionally this is V divided by I, and that is this quantity, which is in turn written as so this has a real and imaginary part as always. So, this is so in that case the magnitude of this complex impedance now. If we look at a classical resistor, it is for a resistor voltage is in phase with current. So, this is how it is defined, and for a capacitor C is equal to Q by V, where basically you have two capacitor plates and one is holding plus Q charge and other is holding minus Q charge in the two plates. So, then the current here is basically dq dt, that is how it is defined by the concerned researchers. So, it is this now dq, C is Q by V. So, it would be C of dV dt, Q would be equal to CV. So, dq dt would be C dV dt. So, this would be equal to, now if you bring in this dV dt, now we have some expression for V. What is that? V naught exponential I omega t. So, if you bring that, then it would be dV dt would be here so this is in turn you can write V naught exponential I omega t as V as from this expression. So you have here now if somebody wants to, so I have already defined ZR, if somebody by the same token defines ZC which is again V by I, that would be equal to, we have the V and so V by I would be nothing but I is equal to I omega V. So, V by I would be 1 by I omega 1 by I, okay, there is one C, I forgot, okay, there was a C here. So, 1 by I omega C, so that is equal to my multiply both sides by numerator and denominator by I by omega C. So, this is for ZC and this is for ZR. Now, if somebody works, so you have a choice, if somebody works with a resistor and a capacitor and try to find out what is the ZRC. So, then his ZRC, that is, then this would be 1, it will be defined by 1 by ZRC is equal to 1 by ZR plus 1 by ZC. So, this gives to 1 by 1 by ZR. Here I see it is 1 by ZR would be 1 by R, and this would be 1 by ZC would be I omega C, because omega C 1 by ZC omega C would go to the numerator. Now, if one also make note that C is equal to epsilon A by D, where D is the distance of separation between these two capacitor plates and A is the area of the plate and epsilon is the permittivity, and one also notes the fact that R is equal to D divided by sigma A, conductivity and the area, and so these are the classically the C and R are defined for an electric circuit. So, in that case this 1 by ZRC, this 1 by ZRC would be, this 1 by ZRC would look like 1 by ZRC would be that would be then 1 plus I omega RC divided by R, which would be equal to A by D into sigma plus I omega epsilon. Now, if one wants to define a real capacitor, then he has to write it as 1 by ZC is equal to I omega square C, and that is equal to A by D I omega C, and that is equal to A by D I omega, I put a tilde here to define this as a complex capacitance or complex permittivity. So, if one wants to define capacitance that way, so that is also possible. In that case, it would this 1 by ZRC. So, 1 by ZRC, these would be leading to the, I mean, if one equates these two, what they will lead to is the this will lead to epsilon minus I sigma by omega. So, this is something what they will lead to. So, they have so what this is all about is the complex permittivity that is defined this way. Now, if one wants to write the ratio of real to imaginary part of these complex permittivity, that gives the idea of the ratio of energy storage to energy loss in one AC cycle. So, that is how it goes. In that case, the tau would be defined as epsilon divided by sigma. This would be called charge relaxation time, so this is equivalent to time required for a charge to move towards a nearby opposite charge in presence of viscous resistance. So, this is the relaxation time. Now, when it comes to the frequency, see it is like this, that the I mean, if we try to summarize this here, what we are doing, when time varying field is applied, so then this implies, because of this RC mechanism present, there would be a lag in displacement of charges. What you this displacement of charges, you refer this as polarization. Now, if AC frequency is low, in that case this implies there will be sufficient time to there will be sufficient time for dipoles to align. So, this implies maximum polarization can be achieved with highest permittivity. On the other hand, so I mean, what do we look at this? There is a maximum polarization that can be achieved. Now, if this corresponding AC frequency, if this AC frequency is referred as omega naught, say, if this AC frequency is referred as omega naught, then this omega naught would be related to this time scale as omega naught is equal to 2 pi by tau, where tau is epsa by sigma. So this is how, I mean, this is how you have, this is how you treat the AC this AC time scale. This I mean, if somebody wants to know, then what would be the right frequency at which this what would be the right frequency for the droplet to form, then one would go for this equation where the tau is the charge relaxation time, and that is equal to this epsa by sigma. So this primarily gives the idea how you can handle, how you can extend your understanding of this relaxation time. I mean, this tau is equal to epsa by sigma, we have used it for DC electro spray. Now for AC electro spray, there would be a similar RC time scale coming in, and you can define a complex permittivity this way, and still you can come up with the right frequency such that this issue is addressed. Now, what so what we have to, what basically we have to ensure that the applied frequency has to be less than these RC 1 by RC time scale. Okay, and this applied frequency here we are holding it as applied frequency is equal to the time scale. I mean, that is the threshold one that we have to address. Now, this there is another aspect of it which I think is could be looked into here. That is the superposition of AC potential on DC potential. It is not that one has to operate with DC alone or AC alone. What this is talking about is that you can have one can have a so-called disturbance wave, using AC potential. This disturbance wave using AC potential, where this disturbance wave has a frequency associated with the natural frequency of fastest growing instability. I mean, why will somebody do that? I mean, what you are doing is you are superimposing AC potential on DC potential. So why you are doing this is basically you are creating so there is a DC potential existing. On top of that, you are creating a disturbance wave using AC potential at a frequency which is associated with the natural frequency of fastest growing instability. These to benefit, the benefit here is more uniform drop size. So that is what the purpose here is. The next topic that we have here in this slide is something called a DC electrospinning. Basically, the electrospray that emanates from the tip of the conical meniscus that can solidify because of solvent evaporation. So, if that solidifies, if the spray that is coming out, suppose this is the spray that is coming out, and that solidifies because of evaporation, and it leaves behind a polymer strand which is basically a fiber, and the ground electrode that you use, you are supposed to have a ground electrode here, you are supposed to have ground electrode here. So, the ground electrode that you use, if you have this rotating, using a rotating ground electrode, then one can align and get it wound. So, this one can take the strand, align it in the way they want, and do the appropriate winding. So, you can create a fiber out of it. So, as it comes out, these gets, because of evaporation, this solidifies, and so one can get this winding. Now, jet solidifies downstream due to solvent evaporation, that is understood. Random beading, coiling, bending, winding, spiraling, looping, all these are possible due to axisymmetric or azimuthal Rayleigh instabilities. This, I mean, we had this, we talked about these Rayleigh instabilities. That means, if there is a perturbation, that perturbation will grow and it will break this stream at certain points. That is what this instability is all about. But in case of this, I mean, here the jet is evaporating. So, one can expect, I mean, it will not be, there would be an axisymmetric as well as the azimuthal instability. So, if such instability exists, so there would be, if there is an azimuthal instability, of course, you can expect that this jet will have in azimuthal direction some perturbations. Similarly, in the axial direction there would be perturbations. So, they will be reflected in random beading, coiling, bending. I mean, that is what we mentioned here in this slide. And one can control these by the use of ring electrodes around jet. So, one can control these by use of ring electrode around this jet. So that instability is less. So, there are ways to do it, and this is a method, this is known as DC electrospinning. That means, you are producing a fiber of a very small diameter and you are controlling the ground electrode, you are rotating the ground electrode in such a way, so that you are having this, if the winding also over a I mean, in the way you want it, you can align it. So, that is allowed. However, DC electrospinning has these instability problems, and that can to some extent be avoided by using ring electrodes. However, the next slide that I have here is AC electrospinning, and in case of AC electrospinning, you have some major advantage in this regard. Number one, there would be less interfacial charge. This AC electrospinning will have less interfacial charge, and so this whipping instability, and I mean, whatever is arising because of the charge, there was some amount of some instability, those are less. Those problems are less. So, you have, I mean, one can have higher diameter of fiber. That is one possibility. Now, the other thing is, I mean, you got to understand the fact that these there is a AC field operational. There is an AC field which is operational here. So, a cone is formed, and then fiber is ejected, and at the next moment the charge on the fiber is changed. So, I mean, if I try to write this down, a cone is formed in every half cycle, I mean AC cycle we mean, and then fibers are ejected, and fibers are ejected intermittently. And moreover, the charge on each fiber is opposite to that of its the earlier fiber that has come out of it, because there is this AC field. So every time, every half cycle, so one fiber coming out and it has some charge, and then next fiber coming out, it is of opposite charge, and next fiber coming out which is again an opposite charge, that means same charge as the earlier one. So there would be always the fiber that is coming out next would be of opposite charge. So that is because of this. So then there would be more of a fusing of fiber. I mean, earlier, when in case of DC electrospinning, we are talking about winding the fiber on something and holding it the way we want, align it the way we want. But here it is what will happen is the fusing of fiber into interconnected network, forming a monolith with applications in tissue, blood vessel, scaffold, and porous membrane. So there would be so it is basically these fibers are of opposite charge, so they are more prone to forming an interconnected network. So it will form a monolith. That kind of monolith has very good application in tissue as an artificial tissue or a blood vessel, scaffold, or forming a porous membrane even. I mean, because this will form a very good interconnected network rather than a single fiber strand. So that is what is typically what you can expect out of these AC electrospinning. Now there is also another point here, which is a critical polymer concentration that decides whether it is fiber or solidified particle due to evaporation of solvent. So when in case of AC electrospinning, first of all we said that there will not be a single fiber strand that comes out. So it would be small strands, small pieces of opposite charges that are coming out. Now on top of this, if there is evaporation going on simultaneously, there is a possibility that it gets evaporated on the way, and so then in that case there would be a solidified particle rather than a fiber, and that is decided whether it would be a particle or a fiber. That would be decided by the critical polymer concentration. That means if the polymer concentration is high, then it would be more likely to form a particle, because it will be evaporating fast. On the other hand, if there is a lot of solvent in it, the evaporation takes time, so it would be otherwise. So in fact, this method is also considered one method. This is an important method for producing rapidly these polymer microparticles. If one wants to do this is one such method. If somebody works with this close to this critical polymer concentration, then it would be possible that some are particles and some are fibers also, because the accurate control of these process is not that much possible. So what if somebody is working close to the critical polymer concentration, I mean there isn't a very sharp critical polymer concentration for this application. I mean, if somebody works within that range, even what will happen is some would be strands, some would be particles, and what they will end up with is a mixture. So that is a possibility. And then you have these the other issue here is this penetration depth. In case of AC electrospinning that we are talking about here, unlike DC electrospinning, in case of AC electrospinning, the penetration depth of high frequency AC current is small. Penetration depth of high frequency AC current is small. So as a result, the encapsulation of proteins, DNAs, cells, organisms, and other therapeutic molecules can be done in fibers without major damage to biomolecules. Because it is this entrant bulk charge neutralizes rapidly. I mean, you are changing the polarity. So that is why it will not charge will not go deep into the it will not penetrate into the core, and so as a result, if somebody is planning to encapsulate proteins DNAs, this would be a good way of doing it. And this encapsulation is done by two methods. One is electrospray or electrospin, an already stable micro emulsion where dispersed phase is the substance to be encapsulated, or otherwise it could be the co-flow through concentric nozzle where the encapsulant which is a photopolymer dissolved in a solvent goes through outer nozzle and solidify after encapsulation at the downstream by UV light. There is another very interesting, I mean, if we may look into this encapsulation further, but before that I think there is a very interesting phenomena connected with these electrodes and with these with the charges here, which is referred as discharge driven vortices. Discharge driven vortices, this is something like this. If you have an insulator and inside insulator plate maybe, and inside it has a liquid pool. I mean, there is a cavity within which some liquid is sitting, which is common application for microfluidic and other applications. So, if there is a liquid in a cavity on this plate, and then if you bring an electrode, next to this, if you bring an electrode and then bring the tip of the electrode, but don't touch the liquid, but keep it above the liquid, in that case if this is the electrode and if this is the liquid level, one will find that there would be vortices generating like this. The reason is something like this: a sharp metal tip raised to a high voltage, it is raised to a high voltage. Beyond the threshold ionization voltage of the atmosphere, co-ions, I mean, this tip is in the atmosphere, tip is not touching the liquid. Beyond threshold ionization voltage of the atmosphere, co-ions are repelled from the tip and collide with electroneutral air. So, in the atmosphere there are if you go beyond the threshold ionization voltage, that means this atmosphere is getting ionized. In that case, the co-ions are repelled from the tip. So, if this is positively charged, then the positively charged ions, they would be repelled from the tip and they will collide with electroneutral air. Air is otherwise electroneutral and these ions are repelled. So, there will be a corona wind developed due to the momentum transfer. So, because the ionization voltage is reached, so there would be ionization and the co-ions that are formed at the tip. The tip has to be extremely sharp and there has to be very high voltage. These are the primary condition. So, then the co-ions are formed and they are repelled from the tip, and because of this collision of these co-ions with these otherwise electroneutral air, there would be a corona wind forming because of the momentum transfer. So, if somebody holds this, I mean, this has been shown that if somebody holds this electrode sharp tip of the electrode at high voltage, and this is the liquid level, there will be deformation of air liquid interface when corona electrode is mounted vertically above the liquid surface. So, that is something which happens all the time. However, when you have an inclined, if I look at the slide, if we look at the slide, when we have an inclined electrode, the tangential component of the impact leads to interfacial shear. So, this inclined electrode, if you have an inclined electrode here on this node, if here I can see, if there is an inclined electrode, what this will cause is, this will cause tangential component of the impact leads to interfacial shear. If I look at it bigger, this is the liquid level and this is the electrode, and then there would be these coions repelled, and then that would be colliding with the electroneutral molecules, and there is a corona wind forming, and this is, there is a tangential component of this to the surface. Tangential component of the impact leads to interfacial shear. Now, if this interfacial shear is strong enough, then it can overcome the viscous force, and there would be a secondary circulation forming within the liquid. There would be a secondary circulation forming because of this. So, this electrode is referred as corona electrode, and there would be such circulation forming. So, typically this is observed that when one use AC field, the critical voltage for corona discharge is lower compared to the DC fields, because there is a reason to it. There is a permanently, minimum voltage is required with AC because of permanently entrained plasma cloud. As long as the frequency is not too low, that plasma diffuses away, and not too high with respect to inverse RC time scale of plasma charging mechanism. So, we are back to then again this RC time scale. So, you can always, this plasma charging mechanism, that can also be looked into as a resistance capacitance model, and then that will also have its own time scale. It takes some time for the plasma charging. So, the time scale for this AC, that AC time period, that has to be within this framework. See, the minimum voltage is required with AC because of the permanently entrained plasma cloud. That means, in AC you have a permanently entrained plasma cloud already, it's in ionized state sitting there. So, when you are coming back next, you have those available. Now, as long as the frequency is not too low, that plasma diffuses away. See, if it is taking too long to come back, then the plasma diffuses away. That is so that is one issue. On the other hand, if it is too fast, if the AC frequency, that means imposed this imposed AC frequency is too high, that means it is changing too fast, then that will not match the RC time scale of plasma charging mechanism. In that case, it will be difficult to charge the, it will be difficult to create that plasma of the first place. So, there is again a time scale issue here. At high voltage and frequency, at high voltage and frequency, there would be vortex shedding or cascade of vortices or turbulence. So, this is so typically at high voltage and frequency, of course, frequency is within this framework, but high frequency, there these issues, these are the few things that will feature, and these are ideally suited for microfluidic mixing. So, this can be a process by which a microfluidic mixing can be performed. Now, if we try to look into some, if we try to understand applying what voltage, we would be getting what kind of circulation, that would be important. I mean, if I try to sell this, if somebody tries to sell this idea, then that is something which has to be clearly pointed out. Now, here one may start with, I mean, one has to understand that there is no imposed pressure gradient here. So, no imposed pressure gradient in in air around the electrode, and if one uses a steady inviscid flow, for steady inviscid flow, the momentum conservation, first the momentum conservation has to be done with the air. Okay, the momentum conservation in air around the electrode would be rho g UG So, this would be the momentum conservation equation in this case, where rho g is the density, UG is a velocity vector, and we have taken the grad of it, and this rho EL is the charge density. This rho EL, this is the charge density in Poisson equation, density in equation. Now, this has been shown that the UG, the order of this UG comes to this is something what the order of this gas phase velocity, and if one uses I mean if one uses 1 kilovolt as we have done for this electrospray, and one uses say 1 millimeter of here my mind it D is separation between electrode and liquid interface. So, if one takes D as 1 millimeter and V as 1 kilovolt, so in that case what they will get is to the tune of 1 meter per second. That is something that is the velocity one can get, that is as far as the gas phase is concerned. And then if they do the if they use the continuity of tangential stress, if they extend this continuity of tangential stresses at the interface, this if this is used, then one can come up with UL, what would be the liquid velocity at the interface, that would be so this was already there, and then you multiply this. Mu g is the viscosity of the gas and mu is the viscosity of the liquid. So, that is the ratio, basically viscosity of gas divided by viscosity of liquid, and H by R, H is the depth of the liquid chamber. We are talking about a liquid chamber, right. So, H is the depth of that liquid chamber and R is the radius of the chamber. So, that is what is. So, H by R is basically the feature size ratio. So, that is H by R is a geometric parameter, mu g by mu is the viscosity ratio. So, you can work with this UL, and one can see that this UL would be coming to about 1 centimeter. I mean it depends on what kind of geometric ratio you have here. So, I mean it would be it can be related to the gas side velocity, and one has showed that this has substantial liquid side velocity which can give to circulation, that is meaningful. So, the minimum voltage required typically, I mean for this entire analysis we did not consider the AC field etc., but typically if somebody works with the AC field, the minimum voltage required would be about 500 volt at 150 kilohertz. This is for the AC, and for the DC this would be about, this is 500 volt and this is 2 kilovolt for the DC. So, this is the DC voltage requirement, and AC typically this, if somebody uses 150 kilohertz, this would be the 500 volt, and optimum frequency is associated with the inverse. This we have already discussed, that minimum voltage is required with AC because of permanently entrained plasma cloud. As long as the frequency is not too low, that plasma diffuses away, and not too high with respect to inverse RC time scale of plasma charging mechanism. If one wants to work with this, probably 150 kilohertz is a good frequency, and for that one needs 500 volt of voltage. So, that is something we have. One aspect of it which we would like to emphasize here is the use in particle trapping. One big application of this mechanism is the is of course the microfluidic mixing at high voltage and frequency. We have talked about this formation of a vortex. We talked about the formation of a vortex, and then at high voltage and frequency there would be vortex shedding, cascade of vortices, and the turbulence sets in, which is ideal for microfluidic mixing, that we have already discussed. Now, there is another application which has some meaning here, is particle trapping for detection of pathogen in microfluidic devices. The system works something like this, that typically the colloidal particles they are drawn, these colloidal particles are drawn into the vortices because of DEP forces. So, these colloidal particles will be, see this is another mechanism. What we are talking about here is that this is the liquid pool inside the cavity, and the electrode is brought in here, a tip electrode, that this is called corona electrode, a very sharp tip at a very high voltage. So, that is brought in here, and this distance is small. So, here these colloidal particles will be drawn into the so basically this near the interface, the colloidal particles will be pulled by DEP force, so closest to the corona electrode tip. So, they will be coming there. Okay. So, if somebody can manipulate this force at the same time, because the vortex that I have been talking about is generated because of the plasma, and that plasma is forcing the interface, and the interface is creating a viscous shear effect, and so this is moving. This has nothing to do with the DEP attractive force, which is bringing the colloidal particles close to the electrode. So, if somebody can manipulate both these mechanisms, so what they can do is they can pull the colloidal particles. Okay, they can pull them to pull them to the vortex interior. Okay. So, you can focus them in the way you want. Basically, this electrode that can focus the particles, say at the inside the vortex. Okay. So that they can be focused in one place, and some people even have some scientists, they have gone beyond this. There is a possibility to use gravity as well. So they have all these three mechanisms at their disposal. One is this corona wind creating vortex, another is this DEP force pulling these particles in the interior of the vortex, and thirdly there is gravity acting. So all these three forces, they are played simultaneously, so that one can separate the particles from a bulk liquid. I mean, the idea here, this is ideally suited for use in microfluidic devices, because one is that this scheme allows the scheme basically provides play of azimuthal and radial velocity profiles So, they have control over these helical flow, swirl, I mean that can be controlled by using these three mechanisms. So, they can be very effective in separating or you can call it separating, or there is a term commonly referred as trapping erythrocytes, for example, from blood plasma. There are certain advantage to it which the scientists who are working on this scheme they have highlighted. One is the absence of electrode contact. So, the advantage is no electrolytic reaction, and so accordingly no sample contamination. Then the other point is no Joule heating. Then this operates at high frequency. So, the advantage that is put forward is that less chance of electrocution. And another important point, which by now you have already seen this use of this, is that electric field is restricted within the gas medium, and charge does not penetrate beyond the interface. So, the bulk remains primarily unaffected as far as these movement of charges are concerned. So, I mean in other words that this is called field of penetration, or the charge does not penetrate beyond the interface. So, it is if there is any possibility of, so I should write destruction of biomolecules. Destruction of biomolecules that is that can be avoided. That can be avoided. So, if I try to quickly sum up what we have we have looked into recently the electrospray. Then we have found out that there is an issue of time scale, etc. There is an issue of and particularly when you bring in this AC field, then there is this AC frequency, which is another time scale brought in here, and so everything has to be consistent, all these time scales, otherwise you cannot utilize this scheme to the full potential. That is one thing which we need to understand here, and of course there is a critical voltage, there is a critical polymer concentration, so they have to go hand in hand. These are the few things which we fully appreciate. And then we said that there is another new technique which is of course we have differentiated between these forming of fibers or strands and forming of particles, that is that we have done. And what is this AC electrospinning and DC electrospinning, how one is forming a long fiber strand of smaller diameter, and other is forming larger diameter but producing opposite charges, small elements of opposite charges, forming a mesh, forming a membrane, forming a matrix. So these we discussed, and then we brought in another idea, which is discharge driven vortices, where the use of electrode and use of this liquid pool by manipulating this, by forming a plasma cloud, a vortex is created within the liquid pool, and this electrode is at the same time used to pull the colloidal particles using DEP forces, and so and at the same time there is gravity which is always available. So these three forces could be manipulated to create the swirl, create the radial and azimuthal, and all kinds of forces the way one wants, and so this gives a good potential to form the this gives a good opportunity to trap or separate these biomolecules or biological particles in a microfluidic setup. So the potential of this has been highlighted in this lecture. So with that I conclude today's lecture. Thank you very much.